So now we want to fold these Lewis acid bases into our existing descriptions of equilibrium and how they play or interact with everything else we've talked about. So when you have dissolved transition metal cations, they are pretty potent Lewis acids. And so if they're dissolved into solution, they will really serve as an acid for any potential Lewis base, which is really anything with a lone pair. So any sort of molecule with a lone pair anions all serve as good Lewis bases. So Lewis acids will form these complexes, or adducts, means the same thing, with any sort of Lewis base. In this case, silver reacting with ammonia has an equilibrium constant called 1.6 times 10 to the 7th. These equilibrium constants, we call them formation constants, so Kf at the subscript. So formation constants are when a Lewis acid and a Lewis base form this complex ion or adduct, right? We've come together and made one ion. These are usually very product favored, right? 10 to the 7th, really big numbers that we're looking at, pretty big numbers that we're looking at making products. These reactions tend to happen aggressively. So let's look at one implication for solubility. So on lead-2 chloride. How is the solubility of lead-2 chloride affected by a concentration of chloride? KSP of lead-2 chloride is 1.6 times 10 to the negative 5th. So this is something, we now have lead-2 chloride, sorry, lead-2 in our solution. And this is a transition metal cation, sorry, a main group cation. It's not in the transition metals, but it's main group. Still is a Lewis acid, a good Lewis acid. And so it can interact with chlorides to form an ion that's PbCl4 2 minus. So this is an adduct, a metal complex ion in solution, and Kf for this is 2.5 times 10 to the 15th. So if lead-2 chloride dissolves in water, those lead-2 cations are really happy to interact with chloride to form these ions. This is going to happen really aggressively, forming these complex ions. And so it's going to behave as an acid with the chloride, that's the Lewis base. And so if we're looking then at lead-2 chlorides dissolving, well, that'd be Pb2 plus and chloride, right? We can figure that out. And this only depends on Pb2 plus, not the complex ions. So the total concentration of bare Pb2 plus and chloride has to stay low. But if those lead atoms or those lead ions end up, reacting and becoming these complex ions, then that wouldn't fit into this equilibrium constant. So more could dissolve. So we have our reaction of dissolving. PbCl2 reacts to become Pb2 plus and 2Cl minus. Our second reaction then is that the dissolved lead-2 cations react with 4 chlorides to make the complex ion. And so we can put that all together, cancel out the leads, and some of the leads need to cancel out here. The chlorides cancel out to some extent, that 2 and that 4 becomes a 2. And so we're left with just lead-2 chloride solid reacting with dissolved chlorides to yield my complex ion. And now the equilibrium constant for that process is going to be the product of the equilibrium constants for my combined reactions over here, right? Those two are going to multiply together, and I get 4.0 times 10 to the 10th, which is quite an improvement over the KSP of the solid bare PbCl2. So we're going to think about what this is implying. That if I have PbCl2 in my solid form in a solution or exposed to a solution that contains chloride, now I'm going to get an increase in my solubility. Because when the PbCl2 dissolves, the lead cations form transition metal complexes. So more of it is going to dissolve. It's not bare Pb2 plus and chlorides floating around solution, which we know there shouldn't be a lot of. Instead, you're getting this lead chloride complex ion that's floating around solution, not violating it, and you can get a lot of your PbCl2 to dissolve. So we want to put these we've looked at a lot of lead compounds, and PbF2 and now PbCl2, and ways to change their solubility. One of the things we want to be mindful is that lead is very, very toxic. But lead as a metal is very insoluble in water. So that's why we use it as pipes. Theoretically, if you drink water with lead in it, that's really bad for you. But the lead doesn't dissolve, so it doesn't really matter. The lead is just in the pipes. But water in your pipes is not not pure water, so it can do chemical reactions. And there are some chemicals in water that can react with lead to make it into a cation. Right? You get corrosion in your pipes, you get other issues, but lead salts are still very insoluble in pure water. They all have low KSPs. Lead compounds do not tend to be soluble. But we don't tend to have pure water in our systems, right? This is why we need to be mindful of all the reactions. That yes, lead doesn't dissolve in water, but it can dissolve in other things, other solvents that are not pure water, if there's other things in there, if they're acidic, if there's other ions. So when you don't have pure water, lead salts can become very soluble. So lead 2 fluoride, if you have any sort of acidity, all of a sudden becomes soluble. Lead 2 chloride, if there's an excess of chloride ions, all of a sudden becomes soluble. So it's pretty common to have some salt in water, some amount of acidity. As long as we're keeping them low, it should stay low, but this equilibrium constant here is massive. Right, this one, if you have any chloride, you're going to get that to start dissolving, especially if your chloride concentration starts getting really high. And any dissolved lead is bad. It doesn't matter if this is what you're drinking. If you're drinking a complex ion of lead, it's going to cause problems, right? That's still really toxic. We really want to be careful about that. So we can understand this or apply this to something that happened about 10 years ago or a while ago. In 2014, in Flint, Michigan, they changed the water supply. They had water coming from one supply, they changed it to a different supply, and that meant that they needed to increase the amount of chloride in the pipe for disinfection. Basically, they were getting water from a less pure source or a less clean source, so they needed to do more disinfection. In disinfection, Cl2 becomes Cl-. Okay, so that means we had chloride concentrations high in our solution or in our solvent, in the water that's flowing through the pipes. Additionally, because you had really high concentrations of chloride, some of it started to react with the pipes, and it produced lead 2+ cations. Now, you have lead 2+ cations and chloride that's in the solution, so you made insoluble PbCl2. Not the biggest of deal. You might have seen when this happened, there was a lot of discussion of like people had been talking about the water being brown for a while, and this brownness wasn't dangerous. The brownness was an indication that the chloride was basically cleaning out the pipes, if you will, right? It was causing corrosion, cleaning out kind of layers of stuff in the pipes. And as long as the pipes weren't lead, that wouldn't be a problem. But the pipes were lead, and there was continuing high levels of chloride. So basically the initial bits of chloride turn some of the lead into lead 2+. That lead interacts with the chloride to become solid lead chloride. But then you keep having high levels of Cl2. You keep putting a lot of chlorine in the water. So that chlorine, you now have increased levels of Cl-. So you end up with high levels of solid PbCl2 in the presence of Cl-. You start getting large amounts of lead dissolving into the water, going into people's homes. People start drinking it, and through 2015, it starts causing a lot of problems. And so now you're starting to notice effects of lead poisoning in people because they've been drinking this water that was dangerous. The corrosion, the brown stuff wasn't necessarily dangerous. A lot of that's iron corrosion, but there was lead in the system, and so you could also have that there. And so we need to be mindful when we start interacting with chemical systems. There's a lot of complicated parts. A lot of things can interact. And one of the big things that comes from equilibrium is if you can write a chemical reaction down, it can happen. Maybe not a lot, but it can happen a little bit at a time, and over a long period of time that can start to cause problems. Something you might not have intended. No one intended for this to happen, but it did occur. And so we need to always be mindful of what are all the possible interactions? What are all the possible reactions? You have dissolving interacting with Bronsted-Lowry acidity, interacting with Lewis base acidity, these transition metal complexes. Pretty fancy chemistry going on, but in a pretty mundane application that ends up causing a lot of problems. Quite a tragedy. That is it for chapter 15. Started with solubility, kind of really getting comfortable with the solubility products, and then applying in through looking at how equilibria interact with each other. And you can go back and do this for any other equilibria we've ever interacted with. They all are talked about. We've always kind of looked at one at a time, but you can have 2, 3 happening at a time. They all interact, come with a new equilibrium. And then Lewis acids, bases. You thought you were done with acids and bases in chapter 14, but not quite. They came back in chapter 15. They are all around us. And that'll do it. 4 questions on participation 1024. You want to find the 4 of those questions, get them answered, get those answers submitted over on Blackboard by Friday night. Saturday, we'll have the week 9 homework that will cover these chapter 15 ideas. Also, the lab group evaluation is due Sunday. It's going to look exactly like last lab group, but you're only looking at your lab group from this time, right? You're only doing the lab group, the second lab group. So you're not talking about the first lab group, you're talking about the second lab group since the last change. And then next week, you'll be in a new lab group. Check out the notebook to see what your role is for next week's lab, acid-base titration. See what your role is in that. If you have any questions about anything, let me know. Otherwise, enjoy the rest of your day. Answers to participation will go live Friday night. Your test grades will be posted on Friday afternoon as well. If you have any questions, let me know. Otherwise, bye-bye.